All right, this is an utterly fascinating piece of kit that is essentially a slide rule for calculating reinforced concrete. It was the brainchild of Giuseppe Arici, who came up with it in the early 1950s. And this is actually the first model, the Arici T3. The concept of this piece of equipment, which is, by the way, really heavy, it weighs something like maybe 5 kilograms or so for the instrument. It has a bakelite case and plastic indicators, and it has these three white little knobs, and then there is a chrome lever at the side for decoupling the several dials from each other. The concept is, or Giuseppe's idea was, that reinforced concrete is governed by a relatively limited number of equations that couple certain quantities to each other, sometimes by squaring them, sometimes by roots, sometimes simply by multiplication. And by taking logarithmic scales of these quantities, you can rescale them so that the operations amount to, so multiplication becomes addition, and elevation of power becomes a factor in front of the scale. So that means that by gearing these scales together, you can construct the equations that govern reinforced concrete. And this has, of course, several advantages. So what does the machine do? And if you've never seen one and never handled one, I can hardly describe how satisfying this is, because look what happens. If you turn the knob, you see that all the dials are geared together and move together. So in fact, this knob just moves the transparent slider in the middle, and this knob actually does the same as the other knob on the other side. It moves all of the dials. This changes if you uncouple the dials from each other. Then what happens is that this dial moves just the slider with the outside dials of the middle dial. So you see what the difference is. And if you uncouple this, then only the middle dial moves together with this slider. So this allows to change the coefficients of the equation that you are studying. So now, to give an idea of course you can read the webpage that I wrote about this, which has some more extensive text about it, as well as the equations in question. But so let's try and figure out what this can be used for, this thing. So the first problem that is mentioned in the manual is trying to choose the height of a beam of reinforced concrete. The height of the beam would be found on the scale D, which is, so we see here a height in centimeters, so this is the scale for the height of the beam. In order to do that, we need to point the scale. So we want, for example, a height of 45 centimeters. So we are now pointing this line to 45 on the H scale. The important coefficients that we need to set are the strength or the force that can be withstood by the concrete and by the reinforcing steel. And we do that on both of these outer scales. We need to point the pointer to the scale that we want to use. both for the steel as well as for the concrete. So the traction force of the steel is represented by, if I move this pointer away a bit, you can see that there are scales from 1000, 1200, 1400, 1600, 1800 and 2000. So we want to point the pointer to the strength of the concrete, the compression stress of the concrete for every scale of the strength of the steel, with a pointer that is designed for a safety factor of 10. So we have the line in the middle that has m equals 10. So let's assume that we want a strength of the steel of 1600, and then we are going to go for a compression stress of the concrete that is 45 on the 1600 scale. Now if we set this to 45 on the 1600 scale, we also need to put the other one at 45 on the 1600 scale. So that would be here. There we go. So now these two pointers are set correctly. The next thing we can do, if we also want to calculate the neutral distance, is to do the same thing on this outer red scale. There we also have to set this pointer for m is 10 to 45 on the 1600 scale, which we have done. So now the essential strengths of the concrete have been entered into the machine. Now we have to check that our height of the beam, well, that has of course changed, so we bring it back to 45. And now we need to change the round transparent disc over here, where we want to set the diameter of the steel reinforcement. So we will put the number that we want between these two symbols of the diameter in millimeters. So we set the diameter of the reinforcements to 8. This scale is the bending moment of the beam. And so we point the bending moment of the beam for example, to 5 million centimeter kilograms. And this immediately, for the strengths of the concrete and the armoring of 8 millimeter, points us to a height of the beam of 45. Then we can actually read, if we are careful, we can read the number of stirrups. So we can also read the distance to the neutral axis, which is between 9.5 and 10. And we can also read the number of stirrups from this scale. We can see that we need, this is 30, this is 25, this is 20, so the line is at 24. We need 24 8 millimeter reinforcing bars. What we did not set yet is the width of the beam. The width is also a scale that we can find here. Yeah, that is this. So the width The width is going to be 4 centimeters. That seems a little odd. So maybe for a height of 45, the width would be 3.5 centimeters would suffice. But maybe if we want to make it stronger, maybe 15 million. Then we go back to 45 and pick the beam that was not strong enough. So now we read on the D scale, we need that it can be 12 centimeter wide. So for a width of 12 centimeter and a height of 45, we have a number of reinforcements which are 8 millimeter steel bars, and we now need about 7.5 reinforcements. You can keep playing with this, of course. What you could also do is invert the equation and simply set a certain height and width with a pointer, and then change the scales to arrive at a certain strength of steel or compression strength of concrete. So the equations are very flexible, and you can, by turning the knob, very easily see the scope of the possible solutions which give you, for example, the desired strength of the beam. And there are a number of other equations, so the total number of equations that this machine is geared for is 5. So all 5 of these equations can be put into the machine and simply continuously read depending on how you change the parameters. So in fact, this is a very powerful piece of kit in the pre-computer age, and Mr. Arici was clearly very proud of it, judging by the letters that he sent to promote it. So that's it. It's a very satisfying machine. I bought it on a whim, but I'm very happy I did, because it's really a very excellent piece of kit.